Our next speaker is Dr. Koltko, who got his PhD in the University of South Carolina, and now he is in Denver, Colorado, United States. I'm very happy that he came from United States to here. So, the stage is yours.
Okay, thank you. I want to thank the organizers for letting me come here and give a talk. Okay, my talk is on the relationship of the Baryonic Tully-Fisher Law and the gauge theory of CPT transformations. And the Baryonic Tully-Fisher Law is an empirical relationship which relates the limiting rotational speed of the stars in spiral galaxies to the mass of the galaxy. Okay, when one plots the mass versus the fourth power of this limiting velocity, one gets a straight line. This is purely empirical relationship, and I'm giving heuristic arguments that show that this comes from the gauge theory of CPT transformations. Okay. All right. So let's see. Page up. No, page down. Okay. So the original motivation for this was the strange behavior that the stars have a limiting velocity. Okay. When they get towards the edge of the galaxy and they don't drop off. All right. And the dark matter paradigm, you're taking a known force and you're sourcing it by unknown invisible matter. All right. Modified Newtonian dynamics, you're changing the laws of physics at some scale. All right. So my original motivation was neither of those things, but to introduce a new force to explain this. All right. And because forces can be obtained by gauging, making global symmetries local, it seemed to me to take the CPT symmetry and make that local and see what happens. Later on, I realized that what I was actually doing is making it an extension of general relativity, not a modification of it. This is not the same thing as modified gravity theories, and this is not the same thing as modified Newtonian dynamics, MOND, either. Okay? We obtain a relationship that looks very similar to MOND, but it's different. Okay? We respect Milgram's intuitive insight, even courageous you could call it, but we disagree with it. All right? Now, the starting point is to realize that parity and time together, PT, is a proper Lorentz transformation. Just like the boosts and spatial rotations that are used to gauge make general relativity in the metric spin connection formulation. Those are also proper Lorentz transformations too. I call them Lorentz rotations. So it would seem that we should include the P and T transformation with that to gauge the entire group of proper Lorentz rotations. Okay, lambda, I'm using it for that. And when this is done in the metric spin connection formulation, a Vierbein field are introduced, okay, to accommodate, make global Lorentz rotations local. And then a metric spin connection is introduced in order to accommodate this. One gets the exact same thing, the Einstein theory, using the Levi-Civita connections, when one uses the metric spin connection as opposed to the Palatini spin connection. Okay? All right, now, continuing this. Okay, so further motivation as time went on, I want to point out a couple of things. PT is not a universal symmetry. CPT is. The charge conjugation operator added to it, okay, changing matter with for antimatter, makes it a universal symmetry, okay? And I want to compare this to string theory. The underlying symmetry of string theory, supersymmetry, has no experimental evidence. CPT has also been verified in our 4 dimensions. There's no need for extra dimensions, unlike string theory, which there's no evidence for any of the extra dimensions that the various string theories require. Okay? Now, a purely theoretical motivation from this is to try to help make a renormalizable theory of gravity. All right? One frequently hears the phrase that relativity and quantum theory are not compatible. This is not true. Special relativity and quantum theory is. Their union gives us the most accurate theory we have, quantum electrodynamics. Okay? It's general relativity that we have problems with when trying to combine it with quantum theory. The CPT symmetry is born from the joining of special relativity and quantum theory. It doesn't come from either one together or alone. It comes from them together. So it seemed to me the CPT symmetry is a bridge that we can use to go from to combine general relativity and quantum theory. All right. Since we can get general relativity from making the global Lorentz rotations local, it would seem to me we should try to make the CPT symmetry local also and bring it along for the ride and see what happens. See if we can get any additional degrees of dynamical degrees of space-time that could help us make a renormalizable theory of gravity. Okay. Now, the new physics really boils down to the three things: the motivation, the transformations, and the choice of Lagrangian. Okay, so since I have a lot of territory to cover in a limited amount of time, I'm going to have to skip some things. Now, the transformations are very important. At first glance, it would seem like we cannot make a local CPT transformation, all right? Because if we go to Minkowski spacetime, we see that it's simply not a local transformation, except near the origin of the Minkowski spacetime. Because we're taking a Dirac's four-component spinner from large x and transferring it to a large minus x or time, okay? We can do this for arbitrary large distances. So it doesn't seem like it's a local symmetry, all right? The other thing to take into account is if we could even make a global symmetry in curved spacetime, it would not be unique, all right? Because think about it. In a curved manifold, we cannot introduce a unique coordinate system, global coordinate system. We have to introduce many of them. In the overlap region of two global coordinate systems, we don't have a unique value for the CPT transformation if we could even make one, okay? In the overlap region, which coordinate system do we use for the transformed spinner, all right? Now, the way we get around this, okay, is we look at the origin of the Minkowski coordinate system and we take the transformation at the origin and we apply that to every to Vierbein of choice as the local transformation. It's a point transformation. We view the Vierbein. At a given Vierbein, we have an observer who thinks, they're at the center of this tiny Minkowski coordinate system, okay? And they will take the CPT symmetry transformation of a global Minkowski system and apply it to their point at their little tiny origin, all right? Now, what that means is that the spinner, we keep the same value at that point, because at the origin, 0 goes to minus 0, right? So it doesn't change. So the observer keeps the value of the spinner, and the only effect of CPT is to multiply by I gamma 5. I'm using the Bjorken-Durell conventions, except for my sigma AB matrices, a tiny difference there. So all that happens, the local at a given point, CPT transformation, is to replace the spinner by I gamma 5 times that, and to flip the coordinate axes of the Vierbein, okay? To flip the flat indices of the Vierbein, just like you would in a Minkowski system, all right? I'm assuming that there is no such thing as a non-trivial anti-spacetime operation. In other words, there's no such thing as anti-spacetime. If you're interested, I tried to make such a thing in my PhD thesis a long time ago. All right? Now, to put this all together, all right, okay, one other thing. Now, the choice of where we want to apply the transformations and where we don't, this plays the same role. This is the spirit of gauge theories, where we have arbitrary, for example, in U1, we make an arbitrary phase from point to point, okay? The CPT symmetry, we only have two choices. We either do it or we don't, okay? So we have to decide how we define that, all right? And in order to do that, I introduce a differentiable function, f, as a parameter to allow us to decide where we want to do these transformations or not. F is not a physical scalar field, okay? This isn't like a lot of theories where they introduce new scalar fields or bimetric tensors or anything like that. F is simply a parameter that allows us to decide where we want to make local CPT transformations or where we do not. Okay? F has to disappear from any physical predictions at the end. Okay? Now, in order to do this, I also introduce heaviside step functions. That's the theta. All right? And I define it that if the argument of the step function is less than 0, the step function is 0. If it's greater than 0, it's 1. And it does not matter what the value is of 0, as it turns out. Okay? So if I want to do a CPT transformation everywhere on the manifold, global, I set this function f greater than 0. And if I don't want to do it, I set f less than 0. Okay? And it turns out, if you look at the Minkowski spacetime, you have the property that if f is less than 0 everywhere, I obtain the untransformed Dirac action. And if I make f greater than 0 everywhere, I get the same thing as a globally transformed Dirac action in Minkowski spacetime. So it has that nice property. Okay? All right. Now, okay. Oops. All right. One other thing. Okay. F has to be differentiable so that this expression makes sense. That's the only thing, the only restriction that I make on it. Okay. Now, originally, I was worried there is no new physics introduced by this. Okay. So what I did is I also included local Lorentz transformations wherever I did the CPT transformation, because I wanted to see if the metric spin connection could accommodate for these local CPT transformations. If it could, nothing new is going on. All right. Then later I realized if I'm gauging the entire group of proper Lorentz transformations, then I have to put in the entire group. Hence, I put in the local Lorentz rotations also. And these are arbitrary functions of the space-time coordinate system. Again, they have to be differentiable and stuff, so expressions make sense. Okay? So in effect, I'm gauging the entire group of CPT lambda acting on the Dirac field to gauge the full group of proper Lorentz space-time transformations. Okay? Now, putting this all together, we have the following transformation equations. Okay? The two fundamental ones are the Vierbein and the Dirac spinner. Okay? If f is less than 0, this term is 1. These two terms disappear, and nothing happens. This is where we decide not to do a CPT, local CPT lambda transformation. If f is greater than 0, these terms disappear. These two terms become 1. And here we see the effect on the Vierbein. The minus sign represents the flip of the coordinate axes, the little tiny axes that an inertial reference frame observer would see at that point. This is the Lorentz rotation that is done to the observer. Okay? And as far as the Dirac spinner goes, I gamma 5, this is the CPT transformation done to the spinner. And this is the local Lorentz rotation that corresponds to this guy that's also done to the spinner. All right? These are the two fundamental transformation equations. The adjoint spinner follows from this, and the metric spin connection follows simply, we take the definition of the metric spin connection, and we just substitute the Vierbein transformations into it, and we obtain the following form. Okay? Nothing happens when f is less than 0. We get I'll show you what this looks like on the next page. And then we get two boundary terms that introduce Dirac delta functionals. okay? So this also requires us to what is the home of the Dirac delta functional? They have to live under a definite integral, okay? So the definite integral that we use is the action integral, okay? The integrating the Lagrangian density over all spacetime. This is a natural setting for these Dirac delta functionals, okay? It's also a good starting point for the path integral formulation of the theory. Okay, so the exact expressions of this can be found in my archive papers, all right? But for future use, this has a nice transformation, just like gauge theories always have. This is a common feature, all right? Let's see here. The other thing we need to know is the volume element, okay? The invariant volume element, how does that transform? It transforms in this manner, okay? Now, depending on how you define the Heaviside step function with an argument 0, it can introduce removable singularities along these boundaries, which are arbitrary, okay? Removable singularities disappear from the action integral. So there are rules to handle various products that appear. And we always drop removable singularities because they disappear in the action integral. Okay? The delta functionals are fatal singularities, as we'll talk about in a little bit. Okay. Introduction of the new gauge field. All right. Variational principles are used, and it's very straightforward, the rules on how to handle the various products containing these guys. Okay, that's in an appendix of one of my archive papers. The use of variational principles shows that we have a non-trivial and non-vanishing variation of the Dirac action. All right? When I introduce the transformation equations into the Dirac-Lagrangian in a curved manifold, non-trivial variations occur that contain delta functionals. And you can also easily show that the metric spin connection cannot compensate for these. This is straightforward proofs. Therefore, one is required to add a new minimally coupled gauge field, x mu. I'm not putting this in ad hoc. This is required if one wants to keep an expanded action which is well behaved under local CPT lambda transformations. Okay? So this is in the 1308 paper on archive. The structure and transformation of the new field turns out to be the following. The x mu I, mu 5, and x mu AB, these are the dynamical field components, just analogous to the metric spin connection. And these are the matrices that are attached to them that multiply the Dirac spinner. Okay? Beta is an artifact from old work. It can be reabsorbed into a definition of x mu. Anyway, this is not ad hoc, once again. In order to have a well-defined transformation of an expanded Dirac action, it has to have this form, and the transformation has to be the following. Oops. Okay. This is how the gauge field transforms. All right. As usual, if f is less than 0, we don't do a CPT transformation. It stays the same. When we do a CPT lambda transformation, it transforms like this. Okay. There is an I gamma 5. There are I gamma 5 terms in here, but they commute with everything in it, so they annihilate each other and disappear. Okay. And then there's boundary terms, these two guys here. And they have the following form. Okay? And these are the two terms from the metric spin connection. So part of the purpose of the x mu field is to get rid of those singularities that are introduced in the transformation of the metric spin connection. All right? And then there's new stuff that appears. Okay? Now, it's a good idea to stop using variational principles at this point. The subsequent calculations become extremely complicated, okay? Showing that x mu is massless is a bit tricky, all right? So what I do is I go to the standard. Once the mathematical rules are established on how to handle these kinds of terms here, all right, we can just go to what I call the operator approach, all right, for lack of better terminology. This is the standard gauge theory type thing people see, all right? The starting point is we rewrite the transformation of the Dirac spinor in this operator here, and this is the same thing that is introduced earlier. From that, one gets immediately the inverse transformation up to removable singularities, which we ignore, the derivative, okay, and this term here. And this is familiar from gauge theories, okay? These things arise and they're used to build things. From that, we can easily show that the total covariant derivative transforms gauge covariantly under these transformations, for example, all right? Things go real quick using this method. Just like all gauge theories, x mu is massless. That's an immediate consequence. That drops out, okay? Oops. Okay. We denote the transformation by the customary u, even though it's not a unitary transformation. If you go back and look at your textbooks, you'll see that there's no need for unitarity. And in fact, the local Lorentz rotations in general relativity are not unitary. And yet we get the theory by gauging the global transformations and making them local. And for future work, we don't need to have a conservation law associated with the global symmetry. Okay, if you go back and look at your textbooks, there's no need for this. Okay, and there's certain interesting physical consequences that will show up at some point. Okay, so because the CPT symmetry, there is no conservation law associated with it. All right, so we emphasize once again, x mu is required in order to construct a well-behaved expanded action. And its structure and transformation properties are not ad hoc. This is not a modified gravity theory. It falls directly out of variational principles. Okay? All right, now, Lagrangian. Okay, this is the last part where we really have new physics. Okay? I want the Lagrangian, the total Lagrangian, to satisfy 4 conditions. Okay? The first one, we want it to be gauge covariant under local CPT lambda transformations. This is obvious, okay? All gauge theories, you want this kind of thing. The other thing we want is the absence of any Dirac delta functionals in the Lagrangian under the CPT lambda transformation. These are fatal. They're non-vanishing, and they also drag in the arbitrariness of F. The boundary between the regions where we do CPT and where we don't. This is not like a global boundary of the manifold or anything like that. These are the ad hoc regions, the arbitrariness that are always present in gauge theories. They have to disappear at the end. Since these don't disappear at f equals 0, they have to, these are fatal. So these types of singularities cannot be present in the Lagrangian under local CPT lambda transformations. Okay, another condition is I want terms which contain the x mu AB to appear on a different footing than solely within this combination here. Okay, the reason is this appears in the covariant derivative. And remember that some of the terms here get rid of the singularities introduced there. So if x mu AB only appears in this combination, effectively, it's just magically getting rid of the singularities which appear in this metric spin connection. Just a fancy way of saying ignore them. Okay? So to give it physical meaning, at some point, these guys have to appear in combinations outside of this. all right, to give it independent physical meaning. It can't only appear in this combination, okay? Now, the last thing I want is I want some components of the new gauge field to appear in both the free field Lagrangian, the Einstein-Hilbert action of general relativity, and the Yang-Mills Lagrangians that we find in the quantum field theories. Okay? I want it to appear in both. This reflects the fact that the CPT symmetry is a bridge between relativity and quantum theory. Okay? I want the field to have its feet in both types. The CPT symmetry comes from both types, and I want the new gauge field to also come from both types too. Okay? So these are the four intuitive rules to come up with making a new Lagrangian. All right? Okay. So here we go. This is the guy that ends up. All right. The first term here, no surprises, right? This is simply the Dirac term written in curved spacetime, right? Here's the spin connection, and then here's the introduction of the new gauge field, all right? So the first term, there are no surprises here. The second term is just the Hermitian conjugate of this guy, so that I can get a total Hermitian action, so I can go into the path integral formulation of the theory, okay? Now, these are the two free field terms that appear, okay? This I call the modified Einstein-Hilbert action. And I'll tell you how I get it. Normally, in general relativity, we take the Levi-Civita connection, we make the Riemann curvature tensor, and then take various contractions of that to get the curvature scalar, all right? If you look at the metric spin connection, you can do the exact same thing and get the exact same curvature scalar, all right, using the metric spin connection, not a Palatini spin connection, all right? And that, you use omega, the metric spin connection. So to obtain the modified thing, I just add on the x mu AB components to this, okay? And drag that along, and I make a new Riemann curvature tensor out of the combination of the two together, all right? The x mu I and the x mu 5 components that are in here from earlier, there's only one thing I'll use that for in this paper, and then I won't discuss other things that this could be physically applicable to. These are the Yang-Mill free field type Lagrangians that appear. More explicitly, this, okay? And here we see, and this is just this comes from the commutator of the covariant derivatives, as usual, all right? There's no derivative of the spin connection appearing, okay? That's an Einstein-Hilbert term. And we see that the requirement that the x mu AB terms appear in a different combination finally than just being dragged along with the spin connection is satisfied with this Lagrangian, okay? One can show that this entire thing is gauge covariant and satisfies all these properties that I wanted it to, okay? Now, okay. The x mu I and x mu 5 field equations are done correctly in the 1308 paper on arXiv. The rest of the equations are wrong because the Lagrangian was wrong. So here, using the Euler-Lagrange variation with respect to x mu AB, we get this field equation here for these components, all right? A couple things to point out. All right, this kappa, this is basically 1 over Newton's gravitational constant. I defined it earlier in this paper. In earlier work, I defined it wrong. I was careless. But this is the dominant term, these three guys, all right? If you look at it closely, though, What this is doing is defining a new metric spin connection out of the combination of the x mu AB field and the old metric spin connection. Okay? So this is actually an identity from that viewpoint. And these terms with the kappa will disappear. And what we have left over is the typical type of free field equation of motion term, a bunch of nonlinear things, and then a fermionic source term right there. And in earlier work I showed that you can decompose this guy into a spin density and two vector currents. Okay? This will be important later on in a little bit. Okay? So this is the straightforward variation with respect to S. I don't include a Palatini variation of the metric spin connection because I'm using, or the spin connection, because I'm using the metric spin connection. If anyone wants to see it, I have it written down. It's straightforward, usual procedure. Then when I vary the Lagrangian with respect to the Vierbein, I get a modified general relativity equation. Okay? This is the Einstein tensor, but instead of written in terms of the metric spin connection, it's a combination of that plus the x mu AB components. And we also get the following for the energy momentum tensor. And this is familiar looking, right? No surprises, okay? The new free field term makes a contribution there. And these are just straightforward variations, all right? Now, I have to make connection with reality, because physics should. Until I get a point source solution for this, an exact solution, and until I get the propagator figured out for the x mu AB equation, I have to make heuristic arguments. Okay, this is unfortunate. The first one is that the force associated with x mu AB is attractive, just like gravity. All right, that's a pure assumption. Until I get the propagator, I can't prove that. But I argue that it's an inverse square law force for the following three reasons. Okay? First of all, x mu AB is massless. That does not guarantee inverse square law behavior, but it's required for that. The second thing is it affects matter, the Dirac spinner, in the exact same way the metric spin connection does, through that combination in the covariant derivative. Okay? And the third argument I use is that the free field term is contained in both a modified Einstein-Hilbert Lagrangian and a Yang-Mills type. And we know from quantum field theory and general relativity, the fields produced by those follow an inverse square law. Okay? So I'm using these three heuristic arguments to claim that the field produced by this, the new gauge field term, the extension of general relativity term, follows an inverse square law also. The mu I and mu 5 components, they are a new force, okay? They're not just extending general relativity, they follow it as a new thing. All right, now, from this, I argue that Fermion chirality is the source term for this guy here is the source term for x mu AB, okay? In the decomposition, we have a spin density and two vector currents, okay? In bulk matter, this stuff cancels out, okay? The spins on the average come out to be 0, and we don't see movement of the fermions, okay? However, neutrinos, this isn't true. They have a fixed chirality. We're taking the massless Dirac neutrino as our approximation, okay, the classical one with fixed chirality, all right? The actual reason I do that is that the x mu I and x mu 5 components that I'm ignoring if you take their field equations and simply add them and subtract them, you get two new fields, all right? The source terms being right-handed and left-handed chirality. So that's the hint that chirality is important, okay? And that's in the 1308 paper. All right, so using that hint that chirality is important, even though those field equations completely decouple from the metric spin connection and the x mu AB field equations, it's a hint to look at chirality. So we see that the neutrinos produced by the fusion reactions have a fixed chirality, all right? And imagine an observer, you model a disk galaxy, or a spiral galaxy by a radially symmetric disk with a bulge. Someone in the middle sees no net neutrino flux, right? All the stuff coming from the stars hits them and cancels out. As they move towards the edge, then they start to see an increasing flux, until finally at the edge of the galaxy, okay, if that's the center of it over there, that plant, it's all coming from here, okay? So we make a connection with the core cusp problem for dark matter. For these galaxies, the observed matter accounts for the stellar motions from the center out to a certain distance. It's after some distance that you have to introduce the magical dark matter. This is an explanation for that. Okay, I don't have the core cusp problem. The total neutrino luminosity, the flux is 0 at the middle and slowly increases. Okay. Another thing to notice, and this is in a 1308 paper, the dark matter density, when it starts in at some distance, it falls off as 1 over r squared. A massless neutrino also falls off as 1 over r squared. It's almost like an isomorphism. Okay. Dark matter, sourcing gravity versus neutrinos sourcing a new extension of GR. All right. So we don't have the core cusp problem that the dark matter people have. All right. For a massless neutrino, there's only 2 degrees of freedom because the chirality is fixed: the energy and the direction of propagation. For an observer looking at a point source, the direction of propagation is fixed, right? It's just from there to here. So the only degree of freedom is the energy, which is proportional to the neutrino luminosity. Okay? So this will be the source term. We're looking for a weak field limit, a Newtonian form of the new gauge field. The only degree of freedom we have is the neutrino luminosity from all the stars and their fusion going on. Okay? Now, because of the resemblance of the linearized field equation to electrodynamics and the inverse square law behavior that we argue, I can use Gauss's law now, and this is important. We're assuming now the weak field limit, and this should really be an acceleration, okay? And this is really a point source, treating a galaxy as a point source, which is not accurate. This is the Newtonian mass contribution, right? And then this is the new gauge CPT contribution. And QV is this is this constant that's dependent upon neutrino luminosity. And at first glance, it should be exactly the same thing, all right? So we have very reasonably this type of assumption for the total field acting. And we expect, because the neutrinos are ultra-relativistic, and because we can use Gauss's law, we have a problem that's like in elementary electrostatics, okay? We take we draw a Gaussian sphere from a point source to an observer, okay? And everything outside of that makes no contribution, and it's just the stuff in the middle that we can treat as if it's concentrated at the center, okay? Now, because the neutrinos are negligibly interact with anything, and they travel close to the speed of light, we see that the total number of neutrinos is given by the luminosity times the time of emission inside the Gaussian sphere. And that time is just the distance to the observer divided by the speed of light. All right? So we put that in for Q nu into the previous expression, this R cancels out one of the R's in the inverse square law. Okay? And this would be the contribution now. All right? This is where we start to see some resemblance to MOND. Okay? In MOND, at some point, gravitational field or Newton's second law changes to 1 over R behavior. All right? It's important to remember it's still inverse square. The 1 over R behavior comes from this cancellation up here. Okay? The inverse square doesn't disappear. It's the source term. That R cancels one of the R's in the denominator. And at some point, depending on this constant K, the new force constant, inverse square law behavior will always be in 1 over R squared. Okay? And again, in MOND, they have this transition regime where Newton's second law changes into this different form at some tiny acceleration. Okay? I view this as, no, what happens is you just get far enough away and this term will always beat this term, no matter what these constants are. Okay? So we're assuming at the edge of the galaxy that this guy wins, and we equate this, and this should be an acceleration again, sorry. We equate this acceleration to the centripetal acceleration, and we get the flat rotation curve. This is the explanation for the flat rotation curve. All right? Presumably, and this is going to come up later, the one thing we do make contact with MOND, presumably this MOND regime, this acceleration, which is approximately 1.2 times 10 to the minus 10th meters per second squared, that is just when the gravitational force is equal to the gauge CPT force. Okay? So that's what is really going on here. It's not that Newton's second law changes. It's just that they finally tie, okay, in their strength. All right? And we'll make use of this. I have 2 experiments that are not in this paper that I haven't written up yet. And one, Astrophysical Prediction. No, I haven't written these guys up yet. It will be important then. Now, to get the Tully-Fisher law, okay, we assume that a galaxy is primarily made of hydrogen and helium atoms. Okay, those are the 2 big constituents. And a fraction of them are undergoing fusion at any given time. All right? And so the total neutrino luminosity for a given galaxy will be proportional to the mass. It's the number of nuclei that are undergoing fusion. Okay? If I put that back into the previous expression, okay, and I make this proportional to m, all right, and I make a graph of v versus m, I get the wrong slope. I don't get the mass being proportional to the 4th power of velocity. I get it proportional to the square of the velocity. This is really bad, right? Very, very far off. Now, I argue that the real source is not the neutrino luminosity, but the square root of that. Okay? And that gives the correct slope for the Baryonic Tully-Fisher law. Okay? But let me explain to you how I get this. All right? We go back to the field equations. We go back to this field equation here. All right? This kappa here, 1 over kappa, this is proportional to Newton's gravitational constant. So that's a tiny number. So the energy momentum tensor, okay, this guy is strongly suppressed compared to the modified Einstein tensor. So in a weak field limit, we just get rid of this guy. Say it's 0. Okay? Now, the next step is we split up the modified Einstein tensor into 2 pieces. Everything that just contains the metric spin connection remains on this side. Everything else, which contains the the x mu AB components and products of x mu AB and the metric spin connection, we put on the other side of this, okay? Now, using the metric spin connection as the way that we view things, all right, the familiar way. What we have now is we have the normal Einstein tensor, okay, being equal to an effective energy momentum tensor. Effective because it consists of the x mu AB terms, and it's not suppressed by this Newton constant, okay? This shows that the chirality of the fermions bends space-time directly. There's no middleman of an energy momentum tensor, okay? It's simply splitting this up and putting all the x mu AB stuff on the other side, and that acts like an effective source term, okay? That, and if you work that out, you'll see that this stuff containing x mu AB, this goes as the square root of the actual energy momentum tensor, okay? You work out these x mu AB terms, and it goes as the square root of the x mu AB things contained in there. So I take that as a cue that what we really do is we replace this charge thing, not by the neutrino luminosity, which is proportional to the energy, but the square root of that. And that's that argument of splitting up the modified field equation, okay? When I do that, then I get the slope of 4. Exactly like what appears in the Baryonic Tully-Fisher, okay? Now, a few physical phenomena. First, we claim that there is no deviation from general relativity in the extreme gravity environment near black holes. Okay? Because people have watched stars go near them, and they say that general relativity is predicting things, and it should. The reason being, the black hole is not emitting neutrinos like stars are. There's no net, there's an accretion disk that stuff's flying out of, but I think it's safe to assume, because of such high temperatures, there's no fixed chirality of the stuff flying out of it. All right? So I don't expect that there will be any deviations from GR in that type of environment. Okay? The other thing that people bring up is the bullet cluster as invalidating MOND. And they say that the galaxies pass through each other, right? And when they look at the gravitational lensing, the magical dark matter is clustered around the galaxies because it doesn't interact with anything and produces the observed gravitational lensing. There's a bunch of gas and dust that's left over in the middle from this collision that happened a long time ago. Now, it's moving so slow that according to MOND, that should be sourcing the new force, or it should be sourcing gravitational fields that should appear in gravitational lensing, and it doesn't. Okay? Now, for me, there's no problem with this, because the neutrinos produced in the fusion reactions are the source of this bending of space-time. So they follow the galaxies, as they cross through and all the stars in them. So they're attached to that, just like what you see from the gravitational lensing. The stuff in the middle is pretty much devoid of stars, so it's not producing the neutrino emission doing this. Okay? So those are two qualitative things that I want to point out. Okay? The other thing now is I have 2 experimental predictions and 1 astrophysical qualitative prediction that I haven't written up yet. Here's the various references. Okay? My PhD thesis, I was in the quantum theory group at University of South Carolina, headed by Aharonov. Then these are, that's a paper full of typos. I didn't get to see the galley proof of it, so they blew that one. But anyway, these are the 2 archive papers I have I had to get Bekenstein's endorsement for this one. They wouldn't even look at it. They sent this one to 2 different committees before they published it. Anyway, and this is the McGough paper and his collaborators that came up with the Baryonic Tully-Fisher relationship. The original Tully-Fisher Law, 1977, by Tully and Fisher, instead of the total mass, the visible mass, not any hypothetical dark matter mass, okay, of these guys, it was the photon luminosity. And the relationship was the photon luminosity to the 3.5 power instead of 4 being proportional to the velocity to that being proportional to luminosity, okay? But the spread was wider, so this is a tighter relationship, okay? And at first I tried to get the original Tully-Fisher law because I made the assumption that the photons and neutrinos come from the same source, ultimately, fusion reactions in the sun. It takes forever for the photons to bounce out, but they eventually do. But what I forgot was that there's other mechanisms for making photons, like accretion disks in the black holes and then, you know, contractions and stuff, gravitational contractions of the stuff in the galaxy. So they're going to produce more photons than just from the fusion reaction, and that will push the slope from 4 to 3. Anyway, okay, anyway, so here are the new predictions, okay? I didn't explicitly write it down. I was kind of in a hurry to write the paper up, but the last section, this is the form of the acceleration, 1 over r square root. I put an anti-neutrino source here instead of neutrino. The reason being, nuclear reactors, you can view them as little tiny galaxies as far as this is concerned. They're emitting anti-neutrinos instead of neutrinos, okay? The anti-neutrinos come from the decay of the radioactive junk made by the fission processes, and they carry away approximately 5% of the reactor energy, all right? And so they have fixed chirality. It's in the opposite direction. We consider them massless and negligible interaction with matter. So aside from the fact that instead of neutrinos, it's antineutrinos, we should have the exact same relationship as we do for this whole argument with galaxies. Okay? So I can make a potential from that, you know, so it's logarithmic, okay? And what this means is that we should be able to get a gravitational red shift, okay? Just like in general relativity, all right? Except that it will vary with the square root of the power of the reactor, okay? And logarithmically with the distance. So we should be able to take atomic clocks and put them at various distances from a reactor core, okay? And obtain this relationship, okay? Now, I get numbers. This is where I make contact with MOND. Because in MOND, you see expressions like this, okay? A square root of a mass term and 1 over r. And that's because it changes, but for me it's different, okay? As I explained before. It just is kind of a coincidence. So what I do is to obtain this new coupling constant, okay? This isn't kappa from before. This is, you know, a new constant. The force constant, I take the values of the sun, and I take the gravitational field of the sun, and I equate it to this term using the neutrino luminosity. This is the Becquerel value given in a 1989 paper, okay? About 2% of the total photon luminosity is equal to that. I set them equal to each other, and I set them equal to the empirical relationship of MOND. I view MOND as a phenomenological thing, all right? And that's the empirical relationship. And I put the numbers in, okay? And I get a new constant of nature, okay? This is the new force law for the weak field limit. Here's the value, meters divided by square root of kilograms in seconds, okay? And I also want to point, and then, so I put in numbers, okay? Tragically, for a 200 megawatt reactor, the number I get, where is it? It's very tiny, 1.5 times 10 to the minus, I think, 21st value, and there's a logarithmic dependence. And I compare that with the gravitational change in frequency, 10 meters on the planet, our planet, and that is, you know, 1 million times more. Okay, so I think that this is. I think there are atomic clocks that can measure this, but I don't think they're portable. I think you have to build a laboratory to house them. So I think this is just on the borderline of being measurable, a time difference, or it might take 15 months in order to get enough data to show a time difference. But what I realized is the force itself should be measurable, okay? Because this gravitational red shift, there's a factor of c squared. Where is it? There. See, this is what makes it so tiny, all right? So the force doesn't have that. And I worked that out. Okay, well, first of all, here's some numbers. Once I was hoping to explain the Pioneer anomaly with this, okay, because it would seem like here's a new force, it should be able to do it. But tragically, no. Some numbers where the MOND acceleration occurs, the MOND regime begins for our sun, is at a radius of about 10 to the 15th meters, okay? And we see that, you know, an astronomical unit is much smaller. The radius of Pluto is 1 million times smaller. This distance is a little more than a light month, okay? So it's pretty far out there. So I don't expect any solar system deviations to be measurable by gauge CPT, all right? Because you have to go very, very far away to see that. But a reactor, okay, and then here are some numbers to see if I could get it for the Milky Way, and I come pretty close to it, which is good. Now, for a 200 megawatt reactor, here's the acceleration that I expect, and this is measurable. Okay, it's a 1 over r dependence and 10 to the minus 4th meters over second squared. There are gravimeters and accelerometers that can measure stuff this small. This is doable. To take a series of them and space them away from a reactor core and see if it goes as the square root of the power and 1 over r is the distance. This is doable, all right? And should be cheap. The devices exist, all right? Of course, I have to do better. This is for a point source, so I have to figure out, you know, there's rods, how to model for those and their positions and all that. So this is doable. What's the other thing about this? No, I forgot. Okay. Now, the astrophysical prediction requires a type 2 supernova, and this is a qualitative prediction. Since so much of the energy is liberated by neutrinos, one would expect that there will be a spike in a gravitational wave that is detected on the Earth from that blast of neutrinos. And because a neutrino has a tiny mass, that will precede the detection of neutrinos by the neutrino detectors on our planet. Okay? And then there'll be the normal gravitational wave component that they predict for type 2 supernova explosion. All right? So that's a qualitative prediction. There'll be a big spike at the beginning of it due to the neutrino burst. Okay? All right, so, okay, that's it. Thank you.